Hi, I'm Ben, and I modeled duck-mediated dispersal of freshwater bryozoans. For some background, bryozoans are aquatic invertebrates that live in stationary colonies. Freshwater bryozoans can enter a resting state called a statoblast, which allows them to survive in very harsh environmental conditions, including outside of bodies of water. These statoblasts can attach to other animals, such as birds, which then carry the bryozoan colony to other areas. The question I looked at was, how is the distribution of a freshwater bryozoan affected by the dispersal of a resting stage that can withstand harsh conditions, including desiccation? Its removal from its usual aquatic habitat. The model I used to answer this question was of an environment with a permanent lake in the middle, inhabited by bryozoans and ducks, surrounded by dry land that can form ephemeral ponds due to rainfall. There are 11 states a cell can take in the model, but there is some overlap that makes things simpler. The first 5 tiles are simply the environment tiles. In reality, there are only 3 tiles with different states. There's dry land, there's the lake tile, and then there are the ephemeral pond tiles. The lake in the middle of the model is a group of unchanging cells that house the initial population of bryozoans and ducks. Dry land can become an ephemeral pond due to rainfall, and similarly, ephemeral ponds can become dry land due to a lack of rainfall. States 4 and 5 are simply a land tile and an ephemeral pond tile housing a bryozoan colony. The remaining states are simply modifications of previous water cells based on if they have a duck on them and if the duck is currently carrying statoblasts. Moving on to the model specifics, the environment always starts as pictured on the right, with all the ducks in the lake in the middle of the environment. While the initial conditions are the same, as the model is stochastic and the environment cells update before the ducks, the initial ponds are entirely random each run. Additionally, all updates are asynchronous. This is a simplification to prevent ducks from landing on the same cell. The ducks use a more neighborhood and cutoff boundaries when determining their travel. The tunable model parameters are the precipitation chance, the duck travel distance, the carry chance, or the chance that a statoblast attaches to a duck, and the drop-off chance, which is the chance all statoblasts detach from a duck upon landing in a body of water. Moving on to the explicit update rules, lake cells are unchanging and initialized with a duck on top of them. One simplification is that the duck population is stable and equivalent to the number of lake cells. Land cells become ephemeral pond cells with probability equal to the precipitation chance, and each pond tile becomes a land tile with 1 minus the precipitation chance. Ducks can move to any water tile within their travel distance, breaking ties randomly. Ducks in lakes and ponds with bryozoans have a chance to pick up statoblasts, and ducks carrying statoblasts have a probability to drop the remaining statoblasts when they enter any body of water. And to model the resilience of the bryozoan statoblasts, if a bryozoan in its resting state enters a cell, that cell will have a bryozoan population for the rest of the run, regardless of if it switches between a dry land cell or a ephemeral pond cell. As a side note, if I say cell or tile, just know they mean the same thing. To answer my question, I ran 2 tests on my model, one varying the ephemeral pond stability through precipitation rate, and the other simulating the seasonal movement of the ducks by varying their travel distance. Each run was over 100 time steps, taking the average of 50 different trials, with a bootstrap 95% confidence interval for coverage over time, to counteract the stochastic nature of the model. Looking at the first set of results for the pond stability tests, we see some interesting things. The first thing of note is that, as can be seen in Figure 5, the total coverage at the end of the run plateaus at a little over 20% precipitation. This is interesting because it shows that there is heavy diminishing returns, likely due to the randomness of our model. Because of the way our ducks move, having more pond cells early on means that ducks are less likely to enter water with bryozoans, and therefore less likely to pick up statoblasts. Figure 6 reinforces this idea. While there is a tight grouping among all the precipitation rates, we can see that the precipitation rate of 0.1 is significantly below all the others, while all the others are just as tightly grouped as one might imagine. The interesting part of Figure 6 is the very beginning and the middle. We see a sharp jump in coverage from all the precipitation rates above 0.1, but then, from time step 15 to around 50, 0.1 actually has more coverage than all the other precipitation rates. This is likely because the ducks are more concentrated in the areas with bryozoans than in areas without bryozoans because there aren't that many areas available. This likely leads to them returning to the lake more often, compared to if there were more readily available pond cells. Additionally, the rate with the lowest coverage for most of the run is the precipitation rate of 1, meaning all land cells become and stay pond cells for the duration of the run, seemingly leading to overchoice from the ducks, meaning that they spend more time going back and forth between water without ever coming into contact with the bryozoans. These results seem to indicate that there is a sweet spot for precipitation rate, where there are enough stable ponds to distribute statoblasts, but not too many that the ducks are able to avoid areas with bryozoans for long periods of time. Moving on to the second test, we look at bryozoan coverage for various levels of duck movement. For the most part, these results are more in line with what you might expect. As can be seen in Figure 7, there is a sharp increase in total coverage up to around 45 to 50%, after which the increasing travel distance of the ducks does not seem to give any meaningful advantage, with total coverage plateauing a little above 70%. This idea is echoed in Figure 8, where we can see a clear separation of all of the runs where the duck travel distance was lower than 45%, after which there is almost no separation above 45% environment travel distance. One final thing to note is that these runs plateaued at around 73% coverage, where in the precipitation trials, those plateaued around 60%. The default precipitation rate is 10%, and the default travel distance is 25%. So this seems to indicate that a suboptimal travel distance is more detrimental than a suboptimal precipitation rate. Thank you very much for your time.